This lecture is going to discuss both of the approaches to cluster analysis of k-means and hierarchical clustering. So what's the big idea? We can group observations similar to each other together using a distance measure as a proxy for similarity. Cluster analysis is an application of our fundamental notion of similarity. The basic idea is that we want to find groups of objects such as consumers or businesses or whatever, where the objects within the groups are similar, but the objects in different groups are not similar to each other. So we start with something like this, where they're grouped together, and we want each group to be similar to each other, but different, or the items within a group to be similar to each other, but different from the other groups. Observations within a cluster should be very similar to each other, but they're going to be different from the other clusters. It is a common form of unsupervised learning. In unsupervised learning, we are learning from raw data as opposed to supervised learning, where we already have a classification of our examples. That is, we already know our x and y variables. Clustering is going to be a common important task in business for classification, and it's common to attempt to cluster customers into similar groups. So how does clustering work? In k-means clustering, we try to center our observations around a centroid. We will talk about how we will actually go about doing this, but here's a visual of what you would expect to see with k-means clustering, and where the stars here represent our centroids. And then we're going to go through this iterative process where we are trying to find the optimal centroids, where our centroid keeps changing a little bit every time. At each change, when we start looking at which observations are closest to it, and then the centroid will get updated. So it will be an iterative process, and we will see how this is actually done mathematically. But here's an example of it being used in everyday life. For example, if you went to Google News, you could find that there's a clustering already of news articles that you'll see here on the left that are highlighted for you, where there are different types of stories that are already grouped together. They're using a clustering type of algorithm to do that automatically. So they're not going story by story, and by doing that, they're applying an algorithm. So let's talk about the different types of clustering algorithms. K-means clustering approach is a partition algorithm, so here each cluster is represented by the center of each cluster. Later we are going to look at hierarchical algorithms, of which there are two types. There is the agglomerative, which is a bottom-up approach, and then there is divisive, which is a top-down approach. Let's start with looking at how k-means clustering works. First, we initialize the algorithm where we choose key random points as the cluster centers. This means we will have to define how many k's we are going to use. That's how many groups or segments we want to create. So that's something that we end up inputting. Then we're going to assign data points to the cluster center and change that cluster center to the average of the assigned points. Next, we're going to recompute the centroids and repeat step number 3. Then this is going to stop when there's not any more changes in the point assignments. That is, when after changing the centroid, there are not any further points that are going to get reassigned to new groups. So what's happening behind the scenes mathematically? The k-means convergence algorithm that's being used is displayed here. So let's describe what we're looking at. The objective function that we are trying to minimize in this case is the total intra-cluster variance. So there's variance within each of the clusters that we are trying to minimize. The first step in this formula is looking at the differences and the distances between our observations and then the centroid of that cluster. We are ultimately just trying to minimize the total intra-cluster variance through this iterative process. In the end, it will find an optimal solution, and it is going to be guaranteed to find an optimal solution. The most common distance measured is called the Euclidean distance. Because you're looking at a distance measure here, you'll need to standardize the data first before we start our calculations. Now, as far as the different types of distance measures, this slide discusses some of the ways that distance measures between observations can be quantified. Once again, our most common one is going to be the Euclidean distance, like we said before. Manhattan is also another common distance metric that you might see, but there are quite a few as well. And then there are others that we don't have included here that are options for defining the distances between measures. Once again, keep in mind when you're using Euclidean distances that you need to standardize your values, especially if they're on different scales. In addition, I want you to keep in mind with these formulas, the X and Y values in each of these formulas, they're not representing your X and your Y coordinate. They're representing point X and point Y. So now let's look at an example and see how this works. Here we're going to pick K random points on our cluster centers, which are once again going to be our means. So we're going to use K equals 2, and we're going to look at the each of those clustering centers being represented by the X, the red X, and the blue X. So the first step after we've selected where we're randomly going to start is we're going to assign the data points to the closest cluster center. So these on the right go to the red cluster, and those on the left are going to go to the blue cluster. And then the next step, we will change the cluster centers to the average of those assigned points. You can see that the blue point moved down because that's the new average of that area. And then the red one also moved over a little bit. In the next step, we're going to repeat this until we actually get some convergence on minimizing the distances between the interpoints within a group cluster. And then we end up with our optimal solution because this is where it converges. And again, this is where we would draw the line and say that anything to the left is going to be at the blue cluster and everything to the right is going to be the red cluster. So this is what it would look like in an iterative situation. Here we have 3 clusters, and we can see that at each point, which are the centroids indicated with X's, they continue to move as the model tries to minimize the distances within the clusters themselves. And then ultimately at a point where there are not any additional changes in your overall cluster centroid or the assignments of your points. And so that's when we decided that we've gotten to our optimal solution. Here is another example where we have K equals 2. So initially the points were randomly assigned to the centroids, and the points are just arbitrarily partitioned into 2 groups at this point. Then in this case, we're going to start updating our cluster centroid, which is indicated as our black and our blue dot. Next, we're going to reassign the objects based on the new centroid. And here we start to see some of them change. And then we're going to update the cluster centroids again. Then we loop back around if we have to, depending on whether or not the points change along the way. So again, we're going to partition the objects into a number of non-empty subsets equal to our value of K, and then begin to compute our centroids, which are the mean points for each of the partitions, and then assign each object or observation to a cluster of the nearest centroid until there's not any more change. And then at that point, we say that we've reached the convergence of the algorithm. So now let's go through a quick example how this is used in practice. In this example, we're looking at the framework for credit customer optimization based on clustering and predictions. We would start by looking at customer clusters that can be found using data from past credit performance. Within each of the clusters, the expected net present value to the company is going to be estimated. That is, once we cluster them, we're going to look at each cluster and compute the expected net present value of each of those customers in that cluster. Then we're going to use external data to predict new accounts for assessing the probabilities of being in any one of those groups that we created. Then we will be able to predict which group the customers belong to, and then we will have an estimate as to what the net present value of that particular cluster is. In this case, a classification algorithm as well as regression trees are used. The clustering will give us certain groups, and within those groups we can use a regression tree type of algorithm to evaluate the net present value for the customers in each of those groups. So in this case, we're applying clustering as well as looking at the expected value framework to evaluate the potential net present value of a customer in a given cluster And then we're going to predict the cluster a new customer would belong to, so that we can get some insight into the expected profitability of that customer. Next, let's talk about the advantages and disadvantages of the k-means clustering algorithm. So starting with the advantages, it uses simple principles that can be explained without statistical terms. That can be a benefit if you want to explain it to others or convince others to act on your insight. It's also highly flexible and can be adapted with simple adjustments to address nearly all types of shortcomings that you might see. And it's going to perform well under many real-world applications. And it's frequently used in practice, particularly in marketing. The first disadvantage is that it uses an element of random choice. So it's not guaranteed to find the optimum set of clusters. It will find a set of clusters that it is going to minimize the intergroup variance. But because of how it starts, which is based on some random choice of where you set your centroids, it may not actually find the optimal set of clusters. The second one here is that it requires a reasonable guess as to how many clusters naturally exist in the data. So this means that you need to know something about the context of your data. So, for example, if you're trying to figure out how many customer segments you have, you need to take a guess about how many you think you have. And so there is some level of trial and error to see what makes the most sense given the data set that you have. So we don't really have an empirical way to determine the optimal K that we need to use. The last one here is that it's not ideal for non-spherical clusters or clusters of widely varying density. So if your clusters don't have a nice shape to them, then it can create some issues for you in trying to find that optimal cluster. In hierarchical clustering, we use distance matrix as the clustering criteria. This method does not require the number of clusters input, but it needs a termination condition. And there's two types of hierarchical clustering. There is the divisive approach, where we start with all of the elements clustered together as in one cluster, shown here as A, B, C, D, E, and then we work our way backward. And then we have the agglomerative, where step 0 starts with each individual element as its own cluster, and then we work our way forward. With agglomerative clustering or bottom-up approach, you initially start with each data point being considered as an individual cluster. You can first merge the instances that are going to be most similar to each other, and you're going to incrementally build the larger clusters out of the smaller clusters. The algorithm works like this. First, you compute the proximity matrix, and initially each instance is its own cluster. And you're going to pick the two clusters that are closest to each other and then merge them into one new cluster. Then you update the proximity matrix and continue until there's only one cluster left. So you're going to keep going until all of them are in one cluster. It's not going to produce one clustering, but a family of clusterings are going to be presented by a dendrogram. So let's look at what that looks like in action. Here's a visual of what you would see with agglomerative clustering, where what you're seeing are the clusters being put together. So you can see here on the right what it would look like when you were to plot it in a dendrogram. So at the end you end up with one cluster. So first it started with individuals, then you merged two together, and now you merge these two over here, and then you keep clustering until you end up with one cluster at the very top. So this, at the very end of the agglomerative clustering, you have everything together and there's no more clustering that you can do. So it's always going to end with one great big huge mega cluster at the end, starting with one individual element per cluster, where each cluster is in each individual element. Here's another view. So again, we start with an individual observation in its own cluster. The first step is we are going to calculate the proximity of the individual points and consider all the points here as individual clusters. Then in step 2, two similar clusters are merged and formed as a single cluster. And we see here with B and C turned into one cluster and D and E turned into another cluster. Notice that A and F still stay on their own. So now we are left with 4 clusters: A, B, C, D, E, and F. Then again, we're going to compute the proximity of the new cluster and merge similar clusters again. In this case, we now have D, E, and F merging into one. And now we are left with 3. So we have A, B, C, D, E, F. Then we continue to do this. So again, we're going to calculate the approximate measure and merge them again until at last we end up with one mega cluster at the very bottom with all of the observations, shown here with cluster A, B, C, D, E, F. Now let's look at this in a dendrogram. For a dendrogram tree, its horizontal axis indexes all of the objects in a given data set. So here we have A, B, C, D, and E. The vertical axis expresses the lifetime of all possible cluster formation. The lifetime of a cluster is defined as the distance interval from the moment the cluster is created to the moment that it disappears with a different cluster. So in this case, in the beginning, we again have 6 clusters: A, B, C, D, E, and F. Then we merge clusters D and F first, and we form one. So the distance is going to be 0.5 because it goes from 0 to 0.5 on our axis. Then we merge clusters A and B into AB, and the distance for that is 0.71. And we merge clusters E and DF into clusters DF and E, and that distance is 1. We keep going here with the next one having a distance of 1.41 when we merge them, and so on. So we compute the distance between when it was created all the way up through when it was merged with the next cluster. And don't forget that the last cluster will contain all of the objects, and we're done with our computation at that point. So divisive hierarchical clustering is not very much used very often in the real world. So I'm only going to give you a brief review of this concept. By definition, it's the opposite of agglomerative hierarchical clustering. We consider all of the data points as one big cluster at the beginning, and at each iteration we separate the data points from the cluster, which are not similar to each other, and each data point is separated, and it's going to be considered as an individual cluster. So in the end, we're going to be left with n number of clusters, with n being however many objects we have in the data set. And so this is going to be considered a divisive approach because we are dividing a single cluster into n number of clusters. Now let's look at a visual of these two methods that we just reviewed. The agglomerative hierarchical clustering starts with each individual element in its own cluster. Then we work our way down until we are all in one cluster. And that's what the dendrogram would look like here on the right. For divisive hierarchical clustering, we start with all of the elements in one megacluster. Then we begin dividing them until we end up with n clusters, with once again n being the number of elements in the data set. And we are going in the reverse order. And so here's what that dendrogram would look like. Now you may be asking, how do you measure the distances between the different clusters? And there are many ways to measure distances. Here are just actually a few of them, and there are actually a few more as well. We have the single link, which is the smallest distance, a complete link, which is the largest distance between elements, an average. There's one called Ward's method. There's the centroid and the madoid. But the one thing that you just need to keep in mind is the different choices are going to create different clustering behaviors. So you really need to be careful of which approach that you're going to use and the effect that it has on your final result. All of the approaches calculate the similarity between clusters, and they all have advantages and their own disadvantages. So there's not always going to be one best method to use. So this would be an example of the dendrogram would look like if you were to use average, farthest, and nearest approach for a particular data set. So you can see that the shapes are all very different, which is going to indicate that you get very different clustering behaviors depending on the distance measures that you use.